Welcome to this electrochemistry lesson. Today, we will unpack the core ideas of redox chemistry, how electrolytes conduct electricity, and how cells like batteries and fuel cells capture chemical energy. Let's get started. First, redox reactions involve the transfer of electrons. Here we depict a simple salt bridge setup with a metal losing an electron and a nonmetal gaining it. The electron flows from the reducing agent to the oxidizing agent, and that movement defines the reaction. Now, electrolytic solutions conduct because ions shuttle charge. Each positive ion moves toward the negative plate, and each negative ion moves to the positive plate. We show a simple beaker with plates and arrows to reveal how current flows. Conductivity depends on how much solution you have. Specific conductance uses the actual cell dimensions. Molar conductance adjusts for the amount of substance, so we divide by concentration to see intrinsic ease of flow. When concentration increases, ions crowd together. So conductivity does not grow linearly. At low concentration, conductivity increases steeply. At higher concentration, ions hinder each other and the slope flattens. Kohlrausch's law tells us that at infinite dilution, molar conductivity is the sum of ionic conductivities. Mathematically, lambda naught equals lambda cation plus lambda anion minus correction. Electrolysis drives non-spontaneous reactions using an external voltage. Here, the power source pushes electrons from the anode to the cathode. Faraday's law says mass of substance deposited equals current times time times molar mass divided by number of electrons and Faraday constant. Let us compare cells. A dry cell uses paste electrolyte. Electrolytic cells need external energy. Galvanic cells produce electric energy spontaneously. A lead accumulator is a rechargeable cell using lead and lead dioxide electrodes. Each discharge releases chemical energy as electrical energy, EMF or electromotive force, equals the potential difference between electrodes when no current flows. Standard electrode potentials give us a reference for half reactions at 1 molar and 25 degrees. The Nernst equation adjusts the cell EMF for non-standard conditions. It reads E equals E degree minus RT over NF times the natural log of reaction quotient Q. We tie thermodynamics to electrochemistry with delta G equals negative NFE. This tells us that more negative free energy change means more cell voltage. Fuel cells convert fuel and oxygen directly into electricity with water as the only byproduct. Corrosion, on the other hand, is unwanted oxidation, such as rust forming on iron. We prevent corrosion with coatings, sacrificial anodes, or inhibitors. That wraps up our tour of electrochemistry. You now know how redox drives cells, how conductivity behaves, and how energy is linked to EMF. Keep exploring these ideas in practice.